Good morning. So today's class is how the MOS transistor work as a switch. As I said in the previous class, the threshold voltage decides when the transistor is in on state and when the transistor is in off. That is, the voltage at the gate, the voltage applied at the gate is less than the threshold voltage of a MOS transistor, then the transistor operates as an off switch. If the applied gate voltage is greater than the threshold voltage, the transistor work as a on switch. Okay, so that is the switching action of the transistor. Now, with reference to switching action of a MOS transistor, there are two concepts we have. One is pass transistor logic and another one is transmission gate. In the pass transistor logic case, what happens is the simple MOS transistor work as a switch. Already we have seen that with the threshold voltage decides comparing the voltage applied at the gate with the threshold voltage of the MOS transistor, we can determine that whether the transistor is in on state or off state. Okay, but we have two different types of MOSFETs. One is N channel MOSFET and another one is P channel MOSFET. Let us see the output values. With reference to output values, what is the state of each and every MOSFET now. Here the diagram representing an NMOS transistor. An NMOS transistor with the applied gate voltage is VDD. Okay, so for this voltage VDD at the gate, that is the gate potential is greater than the threshold voltage, In that case, in generally what happens, whatever the voltage applied at one end of the transistor terminal, the same voltage you can observe at the other end. Okay, but if the in case of logic 0, the same amount of 0 voltage is we can observe at the output in case of NMOS transistor. Okay, but with reference to logic high apply at one end, that is VDD at one end, the voltage at the other end may not be equal to VDD value. It is always less than VDD, that equal to VDD minus VTN because of the threshold voltage. Because of the threshold voltage effect, the output may not equal to VDD. It is always less than VDD, that is equal to VDD minus VTN. Okay, suppose if the output voltage is greater than the VDD minus VTN, what happens is the transistor goes to half state. Okay, so in case of NMOS transistor, if you observe, when it is switched on, it passes logical low value perfectly. Okay, perfectly means whatever the amount of voltage for logical low value at one end, the same amount of voltage you can observe at the other end. Okay, so in logical low case, it is a perfect transmission you can observe, but in logical high case, there is a voltage degradation you can observe. Okay, so that's why finally the conclusion is NMOS transistor is good at passing of logic 0 value but poor at passage of logic 1 value. Right? Now coming to PMOS transistor, it is switched on when the gate potential is 0 volts. With the applied 0 volts, the PMOS transistor is switched on. Okay, in the on state, if the input if the voltage at one end is VDD, the same amount of voltage you can observe at the other end. That is, with reference to logical high, the pass transistor shows the perfect transmission. Okay, but in case of logical low transmission, see, this is the logical low value applied at one end, but the other end we can't get that voltage, that is 0 value. It is always equal to the amount of threshold voltage value, the amount of threshold voltage, that is VTP. So with this, the conclusion is the PMOS transistor is perfect at the transmission of logic 1, but not yet perfect at the transmission of logic 0. Okay, so this is happen because of the threshold voltage of the transistors. Okay, so Nmos transistor is good at passage of logic 0, but Pmos transistor good at passage of logic 1. Okay, so in both the cases we have the drawback. If you use a single MOS transistor as a switch for the transmitting logical values from one end to the other end. So to avoid this drawback, the idea is connecting in parallel these two transistors. Okay, and using complement gate voltages to switch on these two transistors. The resultant gate is referred as the transmission gate. The resultant gate is referred as the transmission gate. Okay, so this is that. This is the transmission gate. It consists both Nmos transistor and Pmos transistor connected in parallel like this. Okay, to switch on Nmos transistor, the gate potential requirement is VDD. To switch on Pmos transistor, the gate is at 0 volts. Okay, so the complement gate voltages it needs. Complement gate voltages it needs. This is the symbol for the transmission gates. Gate. Okay. Now let us see the operation of the transmission gate at two cases. One is at the large capacitive load case and another one is at the small capacitive load. Okay. So here simply the operation is when the gate of Nmos transistor is VDD and Pmos transistor is 0, what happens? Both Pmos and Nmos are in on state. Both Pmos and Nmos are in on state. If the applied value is logical low at one end, the Nmos transistor perfects that value to the output. Whereas if the applied value is VDD at one end, the Pmos transistor transmits that logical one value perfectly to the other end. So that you can avoid the drawback of first transistor, whatever we identified in the previous slide case. Okay, suppose if the Nmos transistor gate potential is 0 and Pmos gate potential is VDD, both the transistor are in half state, that is the output is isolated with the input. Okay, so that is the simple operation. And now see the almost the analysis are transmission gate transistors operating regions with reference to large capacitive load and small capacitive load. Now this slide represents with reference to large capacitive load under two types of transmissions. The first column of figures represents transmitting low to high transition to the output side, whereas the second column of figures represents the transition of 1 to 0, transmitting the transition of 1 to 0. Okay, so first of all let us take the first column diagram. So what it is, under high capacitive load, now the transmission is a transition of 0 to 1 transition, 0 to 1. Okay, 0 to 1 transition. Now we are going to transmit 0 to 1 transition value through this transmission gate under high capacitive load case. So what happens at the input, the transition is very fastly happen. Okay, sudden change you can observe 0 to VDD, but at the output, because of large capacitance value, the output may not change suddenly. Okay, the output slowly varies from logical 0 to logical 1. that is VDD. So that with the VDD input voltage, with the input VDD input like this, at the output you can observe a ramp type of voltage. Okay, ramp type of voltage variation from VSS to VDD. Okay, so with reference to this, with reference to output voltage variation slowly from 0 to VDD, let us see what are the operating regions of Nmos transistor and Pmos transistor, their corresponding resistances. Okay, now this is the diagram represents, okay, variation of output voltage, from very low value to high value, corresponding drain current flow. Okay, suppose when the output voltage is less than VTP, that is the threshold voltages of the Pmos transistor. Okay, when the output voltage is less than VTP, both the Nmos transistor and Pmos transistors are in saturation region. They operate in the saturation region, means the drain current is very high current. In the saturation case, the current magnitude is large. Okay, see, when the output voltage is less than VTP, the currents are very high. This is the IDSN current and this is the curve for IDSP. This is IDSP and this is IDSN current and this is IDSP current. The sum of these two currents is the resultant current. This is the curve representing IDSN plus IDSP. Okay. Okay. Then suppose if the output voltage is greater than VTP but less than VDD minus VTN, the Nmos transistor operate in the same saturation region. The Nmos transistor operates same in the saturation region, whereas Pmos transistor goes to linear region of operation. Okay, you imagine the characteristic curves of MOS transistors. Okay, what is saturation region operation, what is linear region operation, and what is cutoff region of operation. Okay. Similarly, suppose if the output voltage is greater than VDD minus VTN, that is output almost equal to VDD. So what happens? The Nmos transistor goes to cutoff state. I said in the past transistor case, while transmitting logic 1, if the output voltage is greater than VDD, what is the state of Nmos transistor? It goes to half state. Okay, now Nmos transistor go to cutoff, but whereas Pmos transistor operate in the same linear region. Hence, since Nmos transistor goes to cutoff, therefore its current magnitude comes to 0 when V out is greater than VDD minus VTN. Okay, but the Pmos transistor operate in the same linear portion, right? That's why here the current magnitude is like this. VDS peak current is this much amount. Okay, but it is also comes to 0 at higher output voltages. With reference to these currents and operating modes of Nmos and Pmos transistor, with reference to output voltage, the corresponding resistances are like this. Here Rn represents the resistance variation of Nmos transistor, whereas Rp is the resistance variation of Pmos transistor, and this is the curve, the parallel combination of Rp and Rn, equivalent resistance is like this. Okay, with reference to Nmos, the resistance is infinity here. Why? Because the current becomes 0. Current is 0 means the resistance is very high value. Okay, clear? Okay, that is the resistance curve for the transmission gate transistors, Nmos and Pmos. Similarly, let us take the case is the output is not the at the same high capacitive load, but the transmission is a transition of high to low. That you can see in the next class.